Good morning. We are live coding again today, and this time live coding is not actually coding. The topic today is going to be thinking aloud. So we do a lot of benchmarking on various projects that I'm involved in, particularly Snabb and RaptorJIT. And the benchmark campaigns, we want to run them regularly. We do this, before we merge changes onto important branches. And a benchmark is pretty big. It often takes something like, say, 100 hours of CPU time. So it's important to make them run in parallel. And that means, you need to have some computing capability. And at the moment, we're doing this with kind of static capacity, with servers that we own or that we rent by the month. And I want to think about whether now is a good time to introduce a little bit of elasticity and use a bit of cloud capacity to improve things in various ways. So that's what we're going to think about a little bit today. Just try to come up with an overall see what might look like a promising implementation strategy there, if anything. And before we do that, I just want to hop in and recap a couple of things since the last stream yesterday. So one thing is, I'm enjoying doing this streaming, and I find that a lot of the times something interesting happens in passing. We notice something. Maybe we find a bug in some other project that we need to come back to and kind of report and characterize. And I don't want these things to get lost. And I also don't want to kind of stop my flow of the live coding to go and file issues everywhere. So I thought a good compromise would be to just make it easier to reference these videos and come back to them. So yesterday I made a GitHub repository called lukego/live, and every time I do one of these live coding sessions, I just make an issue there, the links to it. So yesterday was the 21st live coding session. So if I click that link, then we get a link to the YouTube video and a place to leave comments. So the thought here is that comments field can actually be quite useful for us. So it's a place after we do some work on a live coding session. This is a place that we can go and follow up. Capture any important notes and reference things. If something happened on a live coding session that is important and interesting for some other group, we could this is where we could kind of reference things. I kind of feel like I do so much with GitHub these days that if something can't be referenced as a GitHub issue or commit or something, then it's almost like it doesn't exist. I think I use a lot of GitHub references like URLs. I love the cross-referencing. So anyway, that's something we have. I'm going to start posting links to the GitHub page on the YouTube pages, and YouTube has its own comments field, but it's crap. You don't have any formatting or anything like that, and I think that you have a kind of an interesting culture there. Anyway, so we're going to use GitHub for major discussions, is my thought. Then I just want to show as well, we've got on Studio, we did quite a bit of work on trying to get continuous integration up and running, and we've succeeded. So the last bit we got to, we solved a long series of issues. And the last thing was a build error where when we tried to run Studio on a CI environment, it would go onto Ubuntu Trusty, and somehow it would end up trying to build the RaptorJIT VM on a file system that was mounted with no exec, and then the VM couldn't bootstrap. And that turned out to be a simple thing where the way we run Studio with Nix shell -- pure, it purges a lot of stuff out of the environment, and it ended up kind of purging the temporary directory, a useful temporary directory. Somehow, when we sanitized the environment, we ended up in another temporary directory that didn't work. So I just did a small fix there. I can show you to just pass in a specific temporary directory. This is the only commit that I pushed after we did stuff yesterday. So now we start Nix shell. It's with an explicit temporary directory. That seems to do the trick. So now the build on Travis went through okay. We got a green mark, and so I'm going to merge that. I'm going to sweep through, pull together all of the various changes that we've got there that are pending, put them all on a branch together, get a green check, and push that onto master. Anyway, that's just to catch you up on what's happened since the last time, so that everything doesn't seem to disjointed. I wouldn't want you to think that we just dropped all of that stuff on the ground. Now onto our actual topic for today. That is elastic benchmarking. So, I'm going to briefly review what is the problem we're trying to solve. I'm going to look at the way that we solve it today, what infrastructure we have, what we've been using for the last few years in Snabb and also a little bit RaptorJIT. and then think about what are some ways that we could improve this in the immediate future. So the problem is that we want to do, basically, mostly is we want to do performance regression tests, or we want to be able to do A/B benchmark comparisons to see if one software version is faster or slower than another software version. And one reason for this is that when we make a release, we don't want the performance to degrade. So it's very important that, you know, release candidates are thoroughly benchmarked to be sure that any performance issues, one way or the other, improvements or regressions, are detected, and we can think about them. And not just for releases, it's also super important for optimizations, right? If you have an idea for some crazy optimization, it's very nice if you can just implement that very quickly and push it somewhere and get a really thorough evaluation to tell you if it's any good. You don't need to think too much about how you would test it and that kind of thing. If you have a really, really comprehensive kind of benchmarking suite, then you can see very quickly. You know, so if you were working on a C compiler, it would be very nice to just run spec-int or something like that, right? You're going to very quickly get feedback on whether this has an improvement for a large representative workload. So the benchmarks that we run, they're all different shapes and sizes, but we're going to use a kind of a platonic ideal of them today. We're going to say that a benchmark campaign usually runs for about 100 hours, and it's made up of a lot of small benchmarks that each take about a minute to run. This is a reasonable approximation. So the way that we run a benchmark is we define a kind of a test matrix with all of the different configurations and software versions and repetitions and everything that we want to test. This can very easily get very large. Each row in the matrix represents about a minute's worth of benchmarking work, and when you add them all up, you end up with about 100 machine hours. You know, so some thousands of rows in the matrix typically, and they can generally be executed in parallel. So we're going to make a matrix of some thousands of tests we want to run, and then we want to run them in some way. And we want that to be a good way. So we'll have a kind of a good benchmarking environment. So in the case of Snabb, actually, often we actually depend on specific hardware. We need like a specific network cards and that kind of thing. We're not going to think about that so much today because we already have that kind of covered with dedicated hardware. But we want to have a pretty pristine environment. We don't want to have a lot of random variation due to other things happening in the background. So for example, if we test on a bare metal machine, then things are pretty under control. If we test on a cloud, there are some issues that can come in, right? There's a hypervisor that can be doing things that are not completely obvious to us. There's contention for uncore resources, you know, like memory and that kind of thing. So we need to be a little cautious about this anyway, because we want to get a very accurate kind of statistical view of performance. And if we get a lot of random variation in the background, this is gonna we're gonna see that, and we're gonna have to probably run more tests to account for it. So we want to have a nice kind of pristine environment. That's one of the things we care about. We also care about kind of throughput, or like the economics of the setup. So we want to have we need to consider the cost of running tests. So if we want to run 100 hours of tests, you know, ideally we would use 100 hours worth of machine time. But if we have static resources, you know, if we have dedicated machines and stuff, you need to pay for them even when you're not using them. So we need to kind of to account for that. We need to make sure that that our capacity is cost effective, even considering, you know, when we're not using it. Or that, you know, that we get reasonable. We got to take utilization into account anyway. And finally, latency is really important. So how long do we need to wait? If we need to run, if we have 100 hours worth of tests, do we need to, you know, if we have just one machine that we want to run it on, then we got to wait 100 hours, which is a long time. If we have 10 machines, we got to wait 10 hours, which is a slightly more reasonable time. It's more like a nightly build. But if we have a few thousand machines, then we can in principle get the result in just 1 minute, right? So this is the appeal of something more elastic. If you would be able to just, if your workload is very parallelizable, as it often is with benchmarks, then it would be, in the ideal case, you would just have you know, one machine for each benchmark, and they would run all in parallel, and you would get your result kind of almost immediately. So we're going to think about, well, I'm kind of sketching solutions and problems at the same time. Anyway, I hope something came across there. We'll be a bit more concrete now. We'll look at a RaptorJIT CI test. So if we pull up the the Hydra continuous integration server. We have CI jobs for RaptorJIT, which is a fork of LuaJIT that we're working on. And we have some benchmarks that check the next branch, the development branch, against the master branch. So if I just pop in, at the moment we get 3 images out of this. We'll take the simplest one first. This is an automatically generated benchmark report that runs automatically anytime anything is pushed to either the master branch or the next branch. And it's making a performance comparison of the next development branch and the master stable branch on a series of benchmarks. This is the Array3D benchmark and the binary trees benchmark and the Kamenios benchmark. So what it does is it has a whole bunch of different benchmarks that it runs. I don't know if it was 20 or so. And it runs each one 100 times. And what you get here is just the results plotted. And this is intended as a way to see are there any differences between the 2 branches on any of the benchmarks? And you can kind of scroll around a little bit. You can also get a feel, like on this roulette benchmark, you can see just, even aside from the comparison, you can see that it's got a bimodal distribution of results. Most of the results are up here, but they're quite often down here as well. So anyway, it's an interesting benchmark. And here, if we've got 100 repetitions of each benchmark times 2 branches, times, what is it, like 20 benchmarks, more or less. What have we got, like 4,000 tests that we run, something like that. So anyway, it can increase. And actually, this represents a really small test matrix because the only variables are the branch, which benchmark it is, and the kind of the iteration count. There's only really 3 variables there. And I would actually like to do a lot more. And on Snabb, we tend to do more elaborate test matrices. So in this case, I would like to also test every different optimization setting separately. I'd like to test in interpreter mode with optimization level 1, with optimization level 2, with optimization level 3 to see if there's any differences there, which can actually be really important. So generally speaking, if you make a change that improves performance on lower optimization settings, that's actually a very, very good thing. It makes things more robust. It means that if any fancy optimizations don't kick in for any reason, that you get better performance. So that's really interesting. I would also quite like to test multiple C compilers and tool chains and that kind of stuff. I'd like to know if we get the same performance with GCC and Clang. Are we sensitive to the optimization settings of the C compiler, that kind of thing. So I could very easily blow this test matrix out to 100 or 1,000 times and actually find that useful, particularly for release tests, to get a really kind of solid overall picture of what's going on. And just, I mean, that picture was a bit hard to interpret, so we actually get a couple more summaries here. This is the same data viewed as a ECDF, an empirical cumulative distribution function, which is just making it a little easier to compare the percentiles. This is on a logarithmic scale and stuff, so I'm not going to dig into this. But anyway, there's of course a lot of different ways you can view data. And we cooked up another one, which I actually feel a bit guilty about this one. I find it quite practical, but it's not really statistically sound. But anyway, this is another one that we do where we aggregate all of the results together and we plot them for the 2 branches as a confidence interval, like where we think we said that this is a bit like a progress meter, where you have elapsed time going this way. You have progress from 0 to 100% of how many benchmarks have completed by that point in time, and this is a confidence band on, when you run the benchmark suite for that branch at a certain elapsed time, what percentage of the benchmarks are going to have been finished. Anyway, so this is a summary of here. These 2 lines, or these 2 confidence regions, are right on top of each other, so it looks pretty clear that doesn't look like there's any real difference. But if there were gaps, that would be more significant. And I'm using significant loosely there, but that's a topic for another time. So what I want to do is a lot more testing like this with a lot more variables. So in the case of this one, I'd like to do about 100 times as many tests to cover like a more satisfying test matrix. So how do we do that? We need hardware to run those tests. And if we hop over and look at the hardware that we have now, keeping our little thing in mind, so we've talked a bit about the problem. Now we're going to look at kind of the way that we run things now. So we have this Hydra CI, which is a kind of a centralized thing, right? So it's shared by a small number of projects like Snabb and RaptorJIT, and it has some hardware resources. machine status. So it's got kind of 3 different kinds of machines. So Grindelwald, this is a machine. It's got like 24 CPU cores and 20 10 gigabit network interfaces and a lot of kind of very particular hardware. There's a few other machines. No, not really on there. So we have a few machines that are very specific. We also have Lugano 1, 2, 3, 4. Those are machines that all have identical CPUs and basically completely identical except for PCI cards. So we can run benchmarks there. We can parallelize benchmarks there and get apples to apples comparisons. And then the most relevant for today are these Muren servers. We have at the moment 10 servers that these are Hetzner machines. So the Lugano servers are machines that we actually own ourselves. We bought and we put the cards in and very generously hosted by Switch in Zurich. Thank you very much. And the Muren servers, these are rented machines from Hetzner, and they're by the month. So at the moment we have 10 machines there, and these are our kind of workhorses. They're all idle at the moment, which kind of says something, right? So these are the machines that normally, if we do a big benchmark campaign, these are the machines that are normally crunching through most of the work. But because this is static capacity, we need to decide each month, or each year, how many servers we want, and then we need to pay for them even when they're idle. So right now all those machines are idle, but we still have to pay for them. And the question with elastic capacity, well, this leads directly into the idea with how we might use elastic capacity in 2 ways. One is if we were using if we were on a public cloud, then if we have no work to do, then we wouldn't be paying for the machines. We just spin them down. It wouldn't be on monthly increments. It'd be more like per minute, which is potentially attractive, and that's especially attractive because it means that instead of having 10 machines, which is kind of like fitting our compute capacity to the amount of work that we need to do. So the reason we have 10 machines is because we actually achieve pretty good utilization over the course of a month. We do run a lot of tests, so they're busy most of the time. So we've dimensioned our hardware according to our kind of our throughput requirements, how much testing we need to do in a month. But if we had an elastic capacity, then maybe instead of having 10 machines, maybe we'd have 1,000 machines or 10,000 machines, because then we could fit the compute capacity to. And I realize that this is not a new idea, but anyway, because then we could fit the compute capacity to the parallelism of our workload. So if we want to run 10,000 tests that make a minute each, in principle, we could fire up 10,000 machines and have them each run for a minute, and then our overall running time would be, not a matter of hours, but it would be a matter of a minute. It would be very quick, and this is people working at Google and these kind of places. This is completely routine for them. But in our CI, we don't have things running that streamlined at the moment. So I'm interested in that specific idea, actually. I'm interested specifically in the idea of taking away the really generic hardware here that's got no special PCI cards or anything like that. They're just Intel CPUs, basically. And moving away from having static capacity and moving towards having elastic capacity. And thinking about how we would do that and how it would fit in with the kind of benchmarking that we do, and also with the infrastructure that we already have. And Another aspect here is the centralized versus decentralized aspect. So now things are very centralized. We have one pool of hardware, and we have one central kind of CI server. So if you want to participate in this workflow, I mean, we do welcome people in. There are a lot of people using this, but we all have to do it as one group, and we're all sharing resources. And as the community grows, it's a bit of a scaling problem. Generally speaking, it's nice to be able to do things independently. If I want to run a huge test campaign, it's nice if I can just go and do it directly. It's a pity if I need to get an account on some specific server, and if I need to ask, is there enough capacity for this, and I need to, worry about relative priority, whether my job's higher or lower priority than other people's, and that kind of thing. So if you want to scale that up, you end up having to create like a foundation that everyone kind of gets bronze, silver, platinum membership in, and all kinds of stuff, and that's just administration that we don't want to do. It's much nicer if we can minimize the centralized aspects and make people more independent. So that's another appeal, I think, to doing things with elastic resources. Instead of having to use one of these 10 servers or all of these 10 servers for your tests, you could just go to your cloud provider of choice, Google or Amazon or whoever, and just run a test and present the results. So let's have a look at the basic candidates for CPU capacity. So I've always been keeping half an eye on the pricing of various kind of cloud CPU thingies, and in the past I have not considered it competitive with the Hetzner servers, but I think that some things have changed. I haven't been tracking it too closely, but it seems to me like in the recent era, Google have made their preemptive machines much cheaper. Preemptible. So I mean, there's a couple of interesting things about the benchmark workload, right? One is that it's extremely parallel. It's a lot of small jobs. The other is that it is preemptible. It's something that you can interrupt. If you wanted to run a minute worth of benchmarks, but you got interrupted after 30 seconds, you don't care. You would just repeat that, so long as the overall rate of it happening is low enough. So it's very attractive in principle to soak up a little bit of this awkward capacity from the cloud providers, short-term capacity, if they're selling it cheap. And I think that this is kind of the case, right? So this is where I'm looking for the basic Google pricing. Now, one question is how much CPU we use, and that's also interesting, actually. Just coming back to the problem. So when we run benchmarks, some of them are happy to run on one core. And then I would kind of mean two of these virtual CPUs, which are hyperthreads, right? So we wouldn't want to be exposed to having funny things happening on another hyperthread. So some of our benchmarks would be happy to have two virtual CPUs, one real core. But others might need more like 8. So for example, for Snabb, some of the basic benchmarks involves recursively running a couple of virtual machines and sending traffic between them. So you have a VM that needs a core and another VM that needs a core, and then you have a Snabb hypervisor switch that needs a core as well. And the VMs might even need more than one core. So some of our benchmarks, different benchmarks have different CPU requirements. For us, it's mostly CPU. And this is another issue when we have static capacity. We kind of need to dimension for the maximum CPU that we need, whereas on an elastic capacity we could kind of have a mixture, which is potentially attractive too. Anyway, just to get a basic feeling for pricing, if we would suppose that a basic RaptorJIT benchmark would be happy on having two virtual CPUs, then the preemptible price of this is 2 cents per hour, which is much less, right? So it's almost 10 cents if you want them to promise not to kind of preempt your VM. So you get a massive discount for accepting this preemptible service level. And for benchmarks, I don't think we care particularly. So being preempted doesn't matter. Although another issue that I don't know, and maybe actually someone listening here does know, and I would love to hear, is how much availability there is there. Like if I would go into my Google console now and ask for 1,000 of these N1 standard 2 preemptible VMs, how many would I actually get? If this is them selling off the awkward in between capacity, do they have a lot of that capacity, or is it just a little? How much? How consistently is this available? That would be really important to know, because we don't want to be in a situation where we have a huge benchmark campaign to run and there's no preemptible capacity available. So that's an unknown that I would like to get to the bottom of. It'd be great if somebody can give me some tips there. Otherwise, it'll be asking around and Googling. So that's Google. And what about Hetzner? So Hetzner is a great company, and they've just launched cloud computing, I think, very recently. So cloud server starting at €2.49 per month. Where do we have the cloud? So Hetzner, they typically have done things, the product I've used from them is monthly rentals on physical machines. You get an actual bare metal machine, no hypervisors, anything there. Just bare metal. Really nice for benchmarking. But the having it fixed all month is a bit unfortunate. So now they have a cloud offering starting at €2.49. So what do we get? Let's compare this with Google. So we were looking at something with 2 vCPUs. We don't really care about these other things except potentially traffic, but I don't think traffic's going to be a big issue, again, for benchmarking, because most stuff is going to be quite self-contained. So I think it's only really CPUs that we're sensitive to. So here, if I understand their pricing correctly, pay by the month, and only if you use your Hetzner Cloud Surf a little bit, you can pay by the hour. So if I'm interpreting this correctly, what they're saying is that while the VM is running, you pay an eighth of a euro cent per hour, and then there's a ceiling of €4.90 per month. So this is you pay this per hour, and then it latches when it reaches $4.90. If I'm interpreting that correctly, so then you would imagine then, I don't know if this is right, but you would imagine then you could set up 1,000 of these. I don't know what really happens if you try to do that. Set up 1,000 of these and actually only pay for the time that you're using them. And I guess you need to. Well, I guess that it's a little bit complicated then, right? If you would want to prefer to use servers where you've already reached the monthly threshold and everything. So how do we... This pricing is a little bit complicated. It might be that there is a really simple solution. For now, let's just do two basic comparisons. The monthly cost versus the hourly cost. So the hourly cost there... 2 vCPUs is an eighth of a euro cent per hour, and on Google we had 2 US cents. Okay, so if I'm interpreting that correctly, I think that we could loosely approximate and say that the Hetzner hold on. 2 cents on Google for a preemptible VM, and Hetzner want nearly 1 cent. Okay, so I kind of had the impression actually that the Hetzner monthly had been more expensive, but it's not true, right? So the Hetzner is less than half the price of the Google one. So if you would pay by the hour, and then what about this ceiling of $4.90? So if you would run it continuously for a month, how does that kick in? So hours per month. Then it's a little cheaper. It goes from an eighth of a euro cent to a sixth of a euro cent. So okay. So then the way to think about the Hetzner price in that case, I suppose, is that it does cost a bit less than 1 euro cent per hour, and there's a modest discount if you run it all the time for a whole month. So the pricing is good on both. For that specific model, Hetzner seems to be about twice as good on pricing, so you get twice the capacity for the same money. And then we just have, for both Hetzner and Google, we have the question of availability. So if I log into a Hetzner account and I create 1,000 of these CX21 instances and I don't start them, and I don't want to pay a cent except when they're actually running, is that a problem or is that fine? Do I have my elastic capacity? Do I have exactly the capacity that I want exactly when I want it and only pay for that? Or is it constrained in some way? And that's a question I'd like to know both for the Google Compute Engine and for the Hetzner. And then I guess the other thing is the Hetzner presumably is not preemptible, which is potentially a plus, although I don't think it matters very much for us. So this is interesting, but ballpark is similar anyway. Okay, and when we talk about ballpark, if we're paying, let's say, 1 cent per hour, and we want to run 100 hours of tests, okay, then we're paying $1 to run a 100-hour test campaign. So if we made a pretty big test matrix that's going to run for 100 hours, that would cost us $1. So every time we want to get a pass or a fail result out of the CI, we'd pay $1, or maybe $2 on Google, if I'm napkin mathing this correctly. And that doesn't seem that terrible, right? Like if you compare that, a lot of things cost $1 in this day and age. So okay, it seems kind of pretty attractive, actually, I got to say. So At the moment, it seems to me like if we could make things run this way, then this would be a pretty attractive way to do things. If we could get even if we could just run 100 servers in parallel instead of 10 servers in parallel, that's a 10 times reduction in latency on the improvement in the turnaround time on our tests. So that would be great. So we don't really need to have 1,000 or 10,000 VMs in parallel. It would be fine to have like 100 or so is probably the point that it becomes interesting. Even 10, well, 100 is where it would get interesting, I think. So, how would the software side of this look? So, the way that we're doing our builds today is we define our test matrix with NICs, which is actually quite nice in several ways. It takes care of all of the software dependencies. It takes care of the runtime dependencies between our benchmarks. So if we do have any kind of dependencies, we can declare them and have it can run as parallel as possible given the dependency constraints, which is actually very nice. And I've also been talking with a clever fellow about some clever ideas for making benchmarks detect when they've run enough to come to a reasonable conclusion, and if we would do that, then the dependency picture would actually become a little bit more intricate, and I think the NICs would actually do quite a good job of capturing that. So I quite like NICs as a way for defining our test matrix and saying kind of what is eligible to run and what is blocked on a dependency. So suppose that we keep NICs as the way that we define our test matrix, and today, in principle, we could run NICs build on a command line, and we could run the test suite manually, locally. So that's something I often do actually with RaptorJIT, just say NICs build and ask it to build the test suite on the current machine, which is fine. The other way that we do it is to run it on the Hydra CI, which does the same thing, but instead of running it on the local machine, it runs it on this pool of servers, statically allocated servers that we have. That is also quite nice, and we would like to retain those two ways of doing things, but we would like to have a third way now. Thinking aloud, well, we could actually, there's a couple of approaches we could take. We could get Hydra to automatically spin up capacity as needed, and I think that the upstream NICs packages does do this. I think that certain changes they make, like they upgrade glibc or they upgrade GCC, I think it needs to go off and rebuild the entire software ecosystem for them. And I think that at those times they detect that they have a really long build queue and they spin up a bunch of extra capacity on EC2 or something like that. So that's one approach that we could take, but that's still very centralized, right? So everything's still going to be getting billed to the same credit card. Everything is still going to be it's not obvious that scales. So it would be nice to have something decentralized, and then it's something that can be used by the normal CI. It can be used independently by people, even if they're working on stuff that's not really relevant to upstream, even if they're working on stuff that's proprietary and they don't want to push anywhere public, and generally just that doesn't require too much synchronization between us as people. It's always nice to be able to be unblocked, not be depending on other people for things. So then I'm imagining we might want to have a third way of running things. So let's just pretend we had a command, instead of NICs build, if we had NICs, let's say cloud build. Suppose we run that, and the first thing it would do is to calculate everything that needs to be built, which would be like running NICs instantiate. Or is it NICs build? Something like that. I can't remember. So you would load the NICs code, which is basically a functional program that returns a test matrix, and you would instantiate that, and that would take the NICs code and evaluate it, and what you would get out the other end would be a specific definition of each individual row in the test matrix, and tracking of all the dependencies, like all of the software that needs to get built to support each benchmark and all, the whole dependency graph. If you would somehow have some benchmarks depending on other benchmarks and that kind of thing, you would have all of that captured in this kind of directed graph that comes out the other end. Then you would kind of want to do then we do the cloud build, right? So we hypothesize, we suppose there was a Nix build minus cloud that takes the result of that. So it would instantiate, and then we would build that on the cloud. And what that would mean is you would need to have some credentials to go out to some cloud, either Hetzner or EC2 or Google Compute Engine or whatever. And it would then need to fire up a suitable amount of capacity. And this would be a basic trade-off depending on how the billing works. So, like, how long does it take to start a VM? If we have a decent image, does it take 10 seconds or 30 seconds or a minute or whatever? There's going to be some startup time on the VM. We're going to need to run that VM for long enough to amortize that startup cost. So suppose we want to run for 10 minutes each VM, and then we want to, beyond that, we want to just have as much width as possible. We want to take as many VMs as we can where we're still expecting to run like 10 minutes worth of tests per VM, and we actually have enough benchmarks in our matrix to run them all. So this would be some kind of a dynamic thing where you start some workers. Maybe workers detect when they're idle if they. Well, you start. There's a lot of different ways you could write this. Suppose that we did this in like a work stealing kind of a way. Suppose that when you did this instantiate step, you get a directed graph of all the benchmarks that need to run, and suppose that this Nix build cloud then would dynamically start some workers. Suppose you start with 10 workers. They all wake up, they all start engaging in looking for work that they can do, just in this directed graph. And if they can take a lock on some job that is not blocked by any dependency, then they can build it, and they're making progress. So we would have some number at any given time. We'd have some number of these worker VMs stealing work from the build graph, and somehow we would need to scale those, right? I'm sure there are clever ways to do it. I'm just as a first approximation. If a worker was starving, if it couldn't find any work to do for a certain period of time, it might shut down. And then on, above that, we might be noticing if no workers have shut down for a while, then they must be pretty well occupied. So we might, start more. And, when we see one shut down, we might back off a little bit because we realize that we've kind of reached the, something I'm pretending it's like TCP congestion control or something like that. Anyway, that should kind of get the job done, I would think. So this instantiate thing is something that already exists in Nix that just creates the graph of all the work that needs to get done. And all we need to do then is a build, and Nix already has some distributed build capabilities that we might even be able to integrate with. But basically all we would need is for the build command to start worker VMs on some public cloud, and to size them in a suitable, elastic way. So we would want to ramp up so that we're running enough VMs to do everything in parallel, but we don't want to get too crazy. We want to make sure that each VM is running for a reasonable amount of time. Anyway, it doesn't sound like that complicated of a program, and very, very, very likely this has already been implemented by somebody, or by 10 somebodies, or by 100 somebodies, whatever. And it's also possible that this could be integrated with some other system, like there's these days you also can get Kubernetes and all of these things from the cloud providers. So it's also possible that some of that infrastructure will be relevant. But if we just suppose that we would need to build this ourselves, it doesn't sound like that much work, right? Sounds like you could almost write it in a couple of hundred lines of shell or something. I don't know. The whole idea seems reasonably plausible. And the nice thing about this would be, as a user, you can just do this completely yourself, right? So suppose I'm working on some super secret, proprietary project that's based on a fork of Snabb, which is Apache licensed, or uses RaptorJIT or whatever. Then I could privately run a build like this on my own kind of cloud resources on my own account, and I don't need to share the results with anybody. It's all mine. And otherwise, if I want to do things upstream as well, I'm still independent. I can run my own tests. It costs me $1 or something to do a test run, which is not really prohibitive. and this would kind of be scalable. You know, if there were 100 people all doing this, and each test cost $1, then it would be a pain. If that all had to be somehow collectively paid for, then it's a barrier. You probably don't want to get involved in the politics of all that, you know, joining a foundation or whatever. It's much nicer if you can just do it. So I think the next step here, I think I would really like to try this out. I think I'd like to get rid of those 10 fixed, completely generic x86 servers that we rent every month, and instead have something a little bit clever like this that that goes out and does things dynamically. And one question we need to resolve is on the compute service, Google or Hetzner, can we actually get the capacity that we want when we want it? In both cases, I don't know. We'll have to find out. People might have relevant experience. And the other question is whether this design actually makes sense, and if so, whether we should implement it ourselves or whether something similar already exists. So I think we'll let this idea percolate a little bit, and we might even wind up this thinking aloud session now. I think we need to push through here anymore. So thanks for joining me in that brain dumping session. It was quite pleasant and hopefully also quite productive. And I return you to your morning.